this video. Alright, so we're going to get into one of the more difficult sections of the book. I teach this in my complex analysis class, or at least these concepts, and so this is a rough section, so please use all your resources to understand this the best you can. For my class, you'll have at least access to these notes and these videos, and then you also have access to the department videos, which George Buck does. So please use both for this one. Alright, so let's talk about this. So polar form complex numbers in De Moivre's theorem. I'm probably saying that horribly wrong. I'll just be honest with you. It's probably French. French did a lot of analysis and stuff in that back in the day, and so it's probably where it comes from. Don't quote me on it. Anyway, so we're going to graph complex numbers. So when we graph complex numbers, we're going to let the x-axis become the real axis. So let's go ahead and mark that as RE. That'll be my real axis and the imaginary axis. So the y-axis is the imaginary, the x-axis is the real axis. And so we call this the complex plane. Now it doesn't quite work the same way as your Cartesian plane, which is x and y. It has a couple other special caveats, but for all intents and purposes, it's close enough that you guys will be okay with it. Alright, so we have the real and imaginary, okay? And so here, so this is called then given, so if we have a z which is equal to a plus bi, so this is the standard form of a complex number, its position in the plane is a comma b. So here, let's just take this sample right here of z. So here, I'm going to go over 2 units in the real direction and 1, 2, 3 units in the imaginary direction, and I go ahead and graph this point. And so this is z1. And we're going to graph this at 2, 3 for z2. We'll do z2 on this one. So we're going to go over 3 units on the real direction, minus 2 units in the imaginary direction, so we have here. And this is z2. And so it's found at 3, -2. Here, if we want to graph 2 times zi, we're going to go over 1, 2, 3, 4, and then we'll go up 1, 2, 3, 4, 5, 6. And so here would be 2 times zi, or z1, sorry. Let me make that a little bit more clear. 2z1. And so it's actually just twice the distance, so if we graph z1 here, 2 times that would just be twice the distance. And notice it kind of lies in the same line right here. That will become important later. And here we can add 2 of them up. So if we add 2 of them up, so we're going to move over 1, 2, plus 3, so 1, 2, 3. And then we're going to go up 3 and then down 2, so it's the same as going down by 1. And so this is z1 plus z2. Okay, and so here we just learned how to graph points. Okay, so this part's not really that bad. The only thing you really need to find here is just you're going to find this is like 2, 3. Here this would be 3, -2. Here if we do 2 times this, it'd be 4 and 6, and so this is at 4, 6. And here, if I add these up, I'll be at 5, -1. Okay. And so this part's not too bad at all. Alright, let's get into the polar form. So that's kind of why we address it now, because we just got done with all our polar stuff. So polar forms of complex numbers is very useful. So it's super useful, so let's make sure we'll go over this. And so here, we have a polar form where we have r cosine theta plus I sine theta. Now where this comes from, you don't need to worry about too much. The absolute value or the modulus of z. So you see the absolute value of the modulus, and so this is the length. That's the absolute of that, so you just take x squared plus y squared. I guess for our purposes, this is a squared plus b squared. Let's go ahead and swap that, a squared plus b squared. And this will be b over a. Okay. Or another way of writing it is the square root of the imaginary number times its complex conjugate. Okay. Convert back. Here I'm using the xy notation. we're going to switch this back to the AB notation. Sorry about that. Another z equals to x plus yi or iy is what we use in analysis. So these end up, it's just the same, just a plus b squared. And so we're going to go over all this and how to do this. Please be careful. Be very careful, since the calculator will not always give correct answers when you use arctangent. So here we want to find the correct angle. But notice arctangent's only going to give us stuff between negative pi over 2 and pi over 2. And so if for instance, when I graphed it, I was here, I need to translate to what this is. Okay. And we've done a lot of this where we've translated to rectangles, and so I'll show you some of this stuff, and we'll go from there. Okay. All right. So let's start here. So let's go ahead and look at this. Let's graph it normally, and then we'll use it. So here we're going to graph it. Let's just graph it first. Let's graph each one of these first. Oh, I left myself room. All right, so here, we'll do like 2 on the same one, just to save space. And so here we're going to do A first. And so here we're going to go in the minus direction, 2, and then we're going to go in the positive. So this is my real axis, this is my imaginary axis. So here, if I graph this, it'd be at minus 2, positive 2, and so this is the point A. All right. And so we have this angle right here. Now, I bet most of you could probably guess what this angle is, right? This is pi over 4, pi, 3 pi over 4, right? But here, if we just kind of tease that out, we'll have tangent of 2 over minus 2, because remember the A is on the bottom, right? If we took the arctan of that, so tangent of theta equals 2 over minus 2. This is sometimes called the argument. So if we took the arctangent of that, we're going to get, we'll get minus pi over 4. And then from this, you're going to have to add a pi. Okay, so we add a pi to it to get the correct angle. Because we want to be in quadrant 2, right? And so notice when I took the arctangent, I ended up here, but notice I want to be here. Okay, so we need to add pi to it. Somewhere, I have a way of always finding this. Let me see if I can find it before the end of this video real quick. In fact, I'm going to make a small cut. Let me just make a cut here. Okay, so I'm going to borrow. I am going to borrow something from Wikipedia, because that's free. And so notice here we have arctangent of x over y if x is positive, right? So here if I have the real part to be positive, you just can take the arctangent normally, right? If the arctangent is negative, right, and y is positive, which we have in this case, you go ahead and add pi to it. If the arctangent is negative, or if x is negative and y is negative, you take the arctangent and minus pi from it. And here, if x is 0, depending on your y, or in this case, this will be our a, so this is a, and this is b. Okay, this wouldn't be a terrible thing to have, nice and comfortable with you. So this is just one way of doing it. All right. Or you can just do what I do and figure it out. But I figured, this one's fun enough as is, so let's just use that. Okay, so now we've added pi to it, and so we get 3 pi over 4. Okay, so here I take the arctangent. Notice that my real part is negative, so I need to add pi according to what I just showed you. So we get this. Then we want to find out what the modulus is. So here we're just going to take this, And we're going to just square both this part. So I have minus 2 squared plus 2 squared is equal to the square root of 8, or 2 square root 2. And so if I was going to write this in polar form, I'd write it as z equals 2 square root 2, comma, cosine of 3 pi over 4 plus I sine of 3 pi over 4. And notice if I actually crunch through this number, I'll get this one back. And so it's a good way to check. Just crunch this number, and you'll get this number back. And so here we go. So this gives us minus 1 over square root of 2. So that gives us negative 2. This gives us positive square root over 2, or 1 over the square root of 2. So this gives us 2. And so notice if we graphed it here, we just go to this angle, and then this distance here would be 2 square root 2. Okay, so here we go to the angle. What angle are we doing? This angle is 3 pi over 4. Okay, and so that's how you do that. Let's go ahead and do this one. Notice, let's do this one. Let's just do these two on this page, these two on this one. So let's do this one. So here, what's my angle? So here I have 3.1 over 0, right? Well, that's not real. Or that's not, you can't do this, right? So tangent of theta equals 3.1 over 0. So this is undefined. But notice that theta is undefined for when it's straight up or straight down. And since this is positive, it will be straight up. And so here, we'll get pi over 2. So that means, hold on, let me just translate. This means that theta equals pi over 2. You can also use the thing on Wikipedia, which I just showed you. Notice that if I take 3.1 squared and then add 0 to it and square it, I'm just going to get 3.1. And so here z is equal to 3.1 times cosine of pi over 2, which of course is 0, plus I sine of pi over 2. And so in this case, it'd be just right here. We just go up, so this is b, so this is pi over 2. And then here, my distance here is 3.1. Okay, so that's how we graph this. Let's do the 4. So here, the tangent, this would be 0, so this would be tangent of theta, oops, hold on, I'm going to do this one time. Tangent of theta is equal to 0 over 4. That just means tangent. And so that implies that theta is equal to 0. Okay, so we have 0. Does that match what we want? Yep. And so 4 square root 4 squared, so this is the modulus, so the absolute value of z, or the modulus of z, is still 4. Same reason here, so it's still 4. So if I wrote this out in polar form, I'll have 4 cosine of 0 plus I sine of 0. So here we have our length, or r, basically, and here is our theta and theta, okay? So here we have our length, r, and then our theta and theta. And so this is just how we write this out. So if we graph this, it'll just be 1, 2, 3, 4 in the x direction, and put it right here. So we'll have the real part and the imaginary part. Alright, for the 5 square root 4. Alright, so what do we do here? So we'll start with our angle, as we've been doing. So tangent of theta. Notice that my real part's negative. So it'll be minus 5 over 1. So here my b is 1, my a is negative 5. My a is negative, so I have to in this case, and my y is positive. So notice I'll be basically here is where I'm graphing d. So this is d, and this is c, right? And so notice again here, you're going to plug this into a calculator, you're going to get some number, then you have to add pi to that number, right? Because you're going to get some negative number. And after you add pi to that number, you're going to get theta is equal to roughly, I'm going to put roughly 2.94. Okay? This is 2.94. And then here, the modulus, or the absolute value, would be the square root of 5, or negative 5 squared, plus 1 squared, gives us the absolute value of 26, or just square root of 26. And that's it. And so I didn't really leave myself room, so I'm just going to write it down here. So here, z is equal to the square root of 26 cosine of 2.94 plus I sine of 2.94. So that's how you write these things into polar form. Okay. So this just takes a little getting used to. Go ahead and have that thing from Wikipedia somewhere. Just write it down. And these are just a bunch of formulas you're going to be working with. Alright, so let's go to multiplication. So why do we put stuff in polar form? Well, the reason we put stuff in polar form is all of a sudden things become real easy. So given two numbers in polar form, so I have z1 in polar form, so I'll have an r1 and a theta 1, and a z2 in polar form, so I'll have an r2 and a theta 2. If I multiply them through some trigonometry, multiplying just means I'm multiplying the radiuses together and then adding up the angles. And if I divide them, it's just multiply as adding up dividing the radius and minusing the angle. So it makes it real easy to do multiplication division. So let's just crunch through a couple of those. Alright, so let's just do 1. So here we have 1. Let's add it and then divide it, right? Convert them to polar and to do that. So let's do the first thing. Convert this to polar. Do we already know what this answer is? Yeah, here, we already did it. But let's do it again real quick. Since I broke in the middle of that one, let's just do this one real quick. So here we have tangent of theta is equal to 2 over, so theta 1 is 2 over minus 2. Notice since this is negative, when I take the arctangent, I'm going to get minus pi over 4. Then I'm going to add pi to it, and so that implies that theta is equal to, let me write out all these steps for you. So if I take the arctangent of theta, I'm going to get pi. So if I take arctangent to both sides, I'll get theta 1, theta 1 is equal to minus pi over 4. But since this is negative, I know I must add pi to it to get the correct answer. So this is 3 pi over 4. Okay. And then once again, this becomes 2 square root 2. And so here we have z1 is equal to 2 square root 2 cosine of 3 pi over 4 plus I sine of 3 pi over 4. And here is z2. z2, since this is in one direction, notice it's pretty much, I think we did it already. And so we have 3.1i, same song, same dance, we're going to just get the same thing. And so here we have z1 is equal to, or z2, I'll put it over here so I have room, is equal to 3 times cosine of pi over 2 plus I sine of pi over 2. So let's do the following. So let's do z1, z2 here, and we'll do z1 over z2 here. So here we're just going to multiply these two together. And so 3 times 2 times square root of 2 is 6 square root of 2. And then we're just going to add the angles. And so it'll be cosine of pi over 2 plus 3 pi over 2, or 3 pi over 4, so this is 2 pi over 4 plus 3 pi over 4 equals 5 pi over 4 plus I sine of, oops, that's a funny looking sign, sine of 5 pi over 4. So once again, we just took this number and this number, multiplied them, and then we took pi over 2 and added 3 pi over 4, that gives us 5 pi over 4, and then we have this. Now when we divide it, or you can just take these two and divide it. So I'll have 2 divided by 3 times the square root of 2, and then I'll have cosine, and here we'll have c1, so 3 pi over 4 minus pi over 2 would just be pi over 4, so pi over 4 plus I sine pi over 4. Okay, so when we add or when we multiply or divide, once we have it in polar form, it's either multiplication and addition or division and subtraction. So it's really not as difficult as it looks. I mean, here it looks pretty complicated, sure, but the actual practice isn't too terrible. All right, let's talk about powers. Oops, somehow this is a typo. Let's go ahead and cross it out. That should be the power of 10 instead of 1, 0. And so convert these into polar form and then use the principal value. So go ahead and skip this. This is leftovers from my complex notes because I did borrow some of it. So for multiplication, aka de Moivre's theorem, for multiplication, we'll just take z to the n is just r to the n times I sine theta. Now, where does this come from? This is easily seen just from the multiplication, right? So if I multiply two numbers, we're just going to, so if I have z1 times z1, this would be r1 times r1. So r1 times r1 would be r2, right? So this would be z squared. So z1 squared would be r2. And then if I add them up, it'll just be 2 theta, right? Now I can just continue that onward. So from here, we get this. Okay? So let's go ahead and figure this out. So let's figure out what this is. So here I have it's 1 and 1. I bet you can guess the angle. So here the angle is obviously pi over 4. Now let's pretend you couldn't guess the angle because here I have 1 and 1. The 1, 1, 1, 1 square root 2 triangle. I hope you really memorized that, because then you could quickly just say z1 or za, I guess, za here. Yeah, let's call this za. Let's call this za, just for kicks. This is equal to za to the 10th power, so 1 plus I is what I'm calling za just for this. So it'll be square root 2 cosine of pi over 4 plus I sine of pi over 4. Okay. Now if we're going to take that to the 10th power, so za to the 10th power, we're going to take square root of 2, raise that to the 10th power, and then we're going to have cosine of 10 pi over 4 plus I sine of 10 pi over 4. Okay? All right. And so what do we get here? So 2 to the 10th power is the square root of 2 to the 10th power is the same as 2 to the 5th. And then, just so I'm not making sure I'm not crazy, let me just double check this with the calculator. You're going to have to do the same. So 2 to the 5th, or you just type in square root of 2 to the 10th power and you'll get 32. Both give you the same answer. All right. Then we can have cosine of 10 pi over 4 but notice cosine of 10 pi over 4 is the same. Oops, hold on, I lost. Why did I lose everything? There we go. I accidentally deleted everything. Alright, and so notice cosine of 10 pi over 4 is the same thing. If I get rid of is the same thing as pi over 2, right? Because it becomes hold on, let me just double check. Let me just do this with me. So this is 5 pi over 2, so it'll be 1, 2, oh, wait a second. 1, 2, 3, 4, 5. Yep, so it'd be the same thing as pi over 4. So this is cosine of pi over, oops, I said pi over 4. I meant to say pi over 2. Cosine of pi over 2 plus I sine of pi over 2. And so once we do all this, can we simplify this? Yeah, this is 0, this is 1, so this is just equal to 32i. So if we took this, and doing this 10 times would take forever, but here when we use our theorem, we get 32i. And let's just double check that in the calculator. And so you can easily just type this in, and I might as well just show you. How to do it in Wolfram Alpha. So let's go ahead and show you how to do this in this. So here I'll have I, or wait a second, 1 plus I to the 10th power. Okay. Yeah, we'll crunch through this, and we get the same answer here, 32i. Okay. So it's just a way for us to do it. Okay, so let's try this one more time. So this is c to the b. I made a small mistake last time, so let's just like that. So here we're going to find the angle. So we'll have tangent of theta is equal to 2 square root 3 over 2. So this goes on top, this goes on the bottom. So the real on the bottom, imaginary on top. This is just the tangent square root of 1 over square root of 3. Notice that my real part is positive, so we can just take the arctangent. So we get pi over 6. Here, if I took, we'll find the modulus, so z. So z equals the square root of 2 square root 3, squared, plus 2 squared. So it'll be 4 plus 4 times 3, which gives us 12. 12 plus 4 is 16. 16, square root of 16 is 4. Alright, so here we'll have z, b is equal to 4 cosine of pi over 6 plus I sine of pi over 6. And then then zb to the 5th is equal to 4 to the 5th cosine of 5 pi over 6 plus I sine of 5 pi over 6. And if I crunch that through, this is 1024, sorry. And this will give me, this gives me a half, and this gives me minus 5 pi over 6. Hold on. Let's not make the same mistakes twice. 5 pi divided by 6, just double checking because my brain just full of not, yeah. This is minus square root 3 over 2, and this is just half. And so this becomes 512 square root 3, or minus plus 512i. Alright, so let's check it. Please check your answers. Alright, and so here I typed it in. And what do we have here? We have this. And so notice even if you type it in this, it gives you a bunch of garbage, so you would have to figure it, because I'm pretty sure I'd want 512 square root 3, and then I. But here you can also notice it will give you in an alternate form. So if you look in the alternate form, it's a good way to figure it out. Alright, so that's how you do that problem. Let's just do the last little bit. Alright, so let's talk about roots of complex numbers. And so, we can do this backwards, right? And we can do this backwards. Alright, so here, if we go backwards, if we take the square roots of something, we can just do something that looks like this. And this just comes from the other one. And so if we take the square root, complex roots of 1, we call this roots of unity, and we can graph them. And so notice that 1 written as a complex number would just be 1 cosine of 0 plus I sine 0. So that's what it is as a complex number. And so what we do here is we take theta, we'll add 2 pi, 2k pi, and we run k from 0 to our n. And so here we're going to take the third root, and so this will be 0 over 3. So our first one is, indeed, so our 0 root. And so here we're going to find the roots. And so we're going to get 3 of them. We're going to have k equals 0, k equal to 1, and then k equal to 2. Alright, and so we're going to go ahead and do that. So k equals to 0. So if k equals to 0, this is going to equal to hold on. Put a little star. I'm going to make another tiny cut here. This is rough. Seriously, go with this crap? Yep. Yep, sorry, I'm just double checking that all of this is exactly it is in the book. It's kind of it's an interesting section to go this deep into it, so let's go ahead and finish going through it, just for completion's sake. Alright, so here if we have 0, so here we're going to start, so 1, so this is always 1, so right here, I'll call this one Z. Define our roots, let's call our roots W. Let's just call the roots W, just use a different character. So W is 0, so here I'm going to plug K into 0, so W is 0. So the cubic root of 1 is still 1, and then here we're going to have cosine of 0 plus 0 pi over 3 plus sine of 0 plus 0 pi over 3. W1 would be 1, because the cubic root of 1 is still 1. Cosine of 0 plus 2, and this time we're going to put in a 1 pi over 3, plus sine of 0 plus, so notice our theta is 0, and then our k here would be 1, so it'd be 2 times 1 pi over 3, and n here is still 3, and then here we'll have W3 is equal to 1 and we'll have cosine of 0 plus 2, 2 pi over 3, plus sine of 0 plus 2 pi over 3. Okay. Alright, so if we crunch through these numbers, so this is just square root of, so this would be 2 pi over 3, and this would be 4 pi over 3, right? And if we crunch through these numbers, we're going to get the following. And so over here, this will just be 1, because this is 0 and 0, so we get 1. The next one here, we're going to get minus, so we have 1 times a minus a half. So 2 pi over 3 gives us minus a half, plus 3 square root 2i. And then this one will give us minus a half minus square root 3 over 2. And this is minus I, if we just crunch to that number. And we're going to go ahead and graph this. I think we're just going to do one of each, just to save time. These tend not to, just because of the complexity, tend not to appear too often. There's more examples in your book that are neither of these. So just for space and time, we're going to just do the 2. Okay? So this is a unity. After we finish this one, I'll tell you what the other one is. And so if we graph this, here we have our first root of unity. W, so this is W1, or W0, this is W1. Our second and our third root of unity. W2. And if I drew it correctly, all of these should be on some sort of circle, right? So let's go put it here and draw it here, okay? So it's all sort of a circle. For the fourth root of unity, the fourth roots are here. And so it's just circles around, and then for the fifth it'll be 5, and so forth. Okay? Alright, so this is roots of unity, and then if you want to just find a cubic root in general, let's go ahead and take this. So here, negative 4, and so we want to find the fourth root of 4, so negative 4, so let's convert this into polar. So I'm going to call this ZB in polar coordinates, and notice notice here, my angle here would be pi, and my distance here is 4, so I can just write that out. So 4 cosine of pi plus I sine of pi. If you have trouble, you can just take z equal to negative 4 and then convert it into polar, and you'll get the same thing. But if you understand where it comes from, you can start writing some of it down. So the fourth root would be to do the following. So here, the fourth root would be to take the fourth root of square root of 4, which would be square root of 2, because square root of 2 times square root of 2 will give you 2, times square root of 2 would be 2 square root of 2, times square root of 2 gives you 4. And so here, the fourth root of 4 is, so here, this will always be square root 2. And here we're going to just be running through, and here we're going to just run through the same thing. So here we'll have W0. So 4, which is, let me just write this out. So our roots, which I'll name W0, W1, W2, and W3. And so notice when we take the fourth root of a negative number, this is complex, right? And so we'll end up getting all the roots, and we end up getting 4 roots, and so this becomes really complex. Once again, I usually teach this in like a 432 class in complex analysis, so I'm going to show you. You might see it on the homework, but you probably won't see it on the final. Okay? So let's crunch through it real quick. And so here, we're going to have square root of 2, and then we're going to have cosine, and then we're going to have pi plus 0, or so 2 times 0, so this will be 0 pi over 4, plus sine of pi plus 0 pi over 4. Here we'll have square root 2 times cosine of pi plus 2 pi over 4 plus, oops, I forgot my I sine of pi plus 2 pi over 4. Where am I getting the 2 pi over 4? Right here. So 2 times 1, so it will be 2 pi over 4. Okay, so the square root of 2 cosine of pi plus 2 times 2, which gives us 4 pi over 4, plus I sine of pi plus 4 pi over 4. And then our very last one will be square root of 2 cosine of pi plus pi over, or 6 pi over 4, plus I sine of pi plus 6 pi over 4. And if I was going to crunch through this, I wouldn't do it by hand. I would just do it in the calculator. I'll show you exactly how I would do it. Alright, so let's show you how to do this in the calculator. Since my current class will be doing this remotely or online, you'll have this option. We're talking about moving everything in the calculator, so you may always have this option. So let's crunch through this. So let's go back to where we were. So we're going to have SQR2 times, and then here we're just putting cosine of pi plus 2 times, in this case we'll have a 0. Actually, I think I can do one better. Let's do one better. Let me show you a couple. Nah, I don't want to confuse you. Let's not do one better. Pi divided by 4. Okay. And so let's just keep this as simple as possible for you guys. I thought about doing something. I was like, let's not throw too much at you at once. Alright, plus, and then I'm just going to copy this. Copy, sign, paste. Oh. I forgot a sign. I was like, why is this wrong? Because I forgot an I. So here, if we plug it in with the I, we should get the correct answer. And here we get 1 plus I. Okay, and then here we're just going to swap this out for a 1, because that's what we do, is just increment our n. We'll get negative 1 minus I. And so let's go ahead and write those in. So here we have not 2, because I forgot the I. It'd be 1 plus I minus 1 plus I. And let's go ahead and finish the last of them. So here we'll go ahead and put in the 2 now. Here we get negative 1 minus I, and then here we put in the 3, and that should give us negative 1 minus I. So here. And so we have minus 1 minus I, and then we have the 1 minus I. Okay, and so that's the end of these notes. This is a really complicated section, so please watch not only my videos, but George's videos. And then kind of learn how to use Wolfram Alpha. And that's the end of this one.